So in trying to find the area between two curves, I keep on having you draw these rectangles. So if we're doing a vertical slice, I get a rectangle here. And then, well, because my top and bottom function change, let me kind of give you a better look at this graph here, like this. But the top and bottom function change a lot as you move from left to right across this figure. So here your top and bottom function change, here again, and then over here. As I mentioned in the first part of this, this kind of thing is a deal breaker. We're not going to be able to take a slice from top to bottom and have it intersect the same curve. It just makes life a lot more difficult. So what this is suggesting is that a dx slice is really not a good idea for this particular function. How about a dy slice? Well, a dy slice is going to run horizontally. So like this. And the nice thing about the dy slice is that in this particular example, our left and right functions stay pretty much the same. In fact, they stay exactly the same. So if I wanted to try and find the area of this one rectangle, well, it's not going to be too bad. So let's see if we can't do that. Here we go. So area of one rectangle. Now instead of doing top minus bottom, I'm going to do right minus left. Minus left. And then instead of having a height being top minus bottom, I'm going to have a height which is going to be the width of this rectangle, which is going to be my dy. So right minus left times, if you want to call it the height, this is your width times the height. That's fine. But now let's see if we can't fill in some things for the rest of this. The height is going to be dy. That's the slice that you're taking. That's also telling you that these two functions that you put here have to be in terms of y. I don't want terms of x because I'm going to be integrating with respect to y. So another reason to have that dy there. It's a reminder. So let's take a look at these two functions. I'm going to look back on this graph over here. The rightmost one is e to the y. The leftmost one is y squared minus 3. So let me put those two together. It's going to be e to the y minus y squared minus 3. And again, be careful that you have to distribute the negative across that y squared minus 3. So overall, e to the y minus y squared plus 3 dy. Okay. Looking good there. That's going to be our integrand. So e to the y minus y squared plus 3 dy. But now we got to work with our limits of integration. What are our limits of integration? And to decide those, you need to decide, well, where can I take this slice and still stay within the bounds of my area? So maybe it's easier to look at here. What should be my limits of integration? -1 to 1. The lowest that this slice can be taken is down here at -1. The highest is up here at +1. So we're looking like that. Let's find an antiderivative from this one. Finish this out. For polynomials, it's okay to do it with fn int, but for these other ones, you're going to have to do it out kind of longhand. So let's see. Julia, what will be the antiderivative for this one, please?
E to the y minus y cubed divided by 3 plus 3x.
3y.
Oh.
Yeah, 3y. Thank you. And that's going to be between -1 and 1. So at our upper limit, we're going to have e to the first minus 1/3 plus 3 minus e to the negative first. Negative 1 cubed is going to be a negative 1, and the opposite of that is going to be a positive 1. So plus 1/3, and then minus 3. If I distribute that negative sign, I'll end up with e minus 1/3 plus 3 minus 1 over e minus 1/3 plus 3 again. Combining like terms, I'll have e minus 1 over e minus 2/3 plus 6, minus 2/3 plus 6, so we can take care of that. We'll end up with e minus 1 over e plus, that'd be what, 5 1/3, which would be 16/3. Nice. Now you can check yourself on a graphing calculator and make sure that numerically that matches your answer that you get from your graphing calculator, but I'd want to see the work done out for this particular one. Are we okay with example G here? Do you understand the need to integrate with respect to y here? At least it's a major convenience. I mean, to do it this way, you'd have to do 3 separate integrals, and you'd have to be a little bit clever in doing this last little bit over here. It'd be a lot more work than just taking a dy slice and doing it that way. All right, let's try another one. Let's try this one down here. Now, one of the problems you're going to face at home is, well, how do I graph this if I can't solve for y? It's not that bad. Let's see if we can't figure out a way to solve this one. Now, in this particular case, x equals y is pretty easy to spot. That's just a line that goes through the first and third quadrants. But the other one, let's see here. The other one, if I solve for x here, let's see, x would equal negative y squared plus 8 all over 2. Or another way to think of that is negative 1/2 y squared plus 4. That plus 4 is going to move the graph to the right. A minus coefficient in front of a y squared term is going to face to the left. So there's your graph. You can find the intercepts of this graph by setting x equal to 0. If you set x equal to 0 and solve, well, I guess you don't really need the intercepts. What we're going to need is these points right here. This is another one for which a dx slice would be problematic. You'd have a function going to itself for top and bottom. So once again, you're probably going to want to take a dy slice. So let's take that dy slice here. And I want your help in this one. I want to find the area of one rectangle. And that area is going to be the right minus the left times the height. So it's the width times the height. What expressions can I fill in for some of this stuff? Joshua, what can I fill in for the rightmost function?
2x plus y squared.
Not quite. Let's tell you what, let's do the height part first. What's the height of this rectangle going to be? dy. So if the height is dy, what else is that telling me about this expression here? Yeah, it can't be any x's. You have to have your expression in terms of y. So that's what we did up here. We solved for x in terms of y. So the rightmost function in this case would be a minus 1/2 y squared plus 4 minus the leftmost function. What should I put in for the leftmost function? Y. Good. Now it's true that y equals x, but because we've got that dy term there, that's telling us we got to put this in terms of y. All right, great. So here's your integrand. Negative 1/2 y squared minus y plus 4 dy. But we're missing one crucial element here. Shreya, what are we missing?
The interval,
Yeah, the interval. How are we going to find the interval?
set them equal.
Yeah, we're going to have to set these two things equal to each other. So, since x equals y, I can make a little substitution in solving these things. So I'll write this instead of 2x plus y squared equals 8, I'll rewrite it as 2y plus y squared equals 8. If I move everything to one side, I get y squared minus 2y minus 8 equals 0, and that factors. How does that factor? Oh, it'd be a plus here, right? It'd be a plus, thank you. So how does this factor? Plus 4 minus 2. All right. So that gives me two solutions. My two solutions are negative 4 and positive 2. Negative 4 and positive 2. Great. Now, it's my personal opinion that I don't want you to get bogged down with a lot of arithmetic. I trust that you can find an antiderivative here. So let's just do the rest of this on our calculator. It's probably convenient to plug things in with an x squared rather than a y squared. You could do the y squared. It's going to give you the same answer. So I'm just going to do math 9, integral from negative 4 to 2. But instead of plugging in things in terms of y, I'm going to plug them in terms of x. Negative 0.5 x squared. And this could be a minus or a plus.
Plus 4 minus y.
Yeah, plus 4 minus y. I'm going to keep them in order. So minus x plus 4. And then go over here and put in your dx. 18. Nice even answer on that one. Beautiful. All right. Comments or thoughts on example H? Looking okay on that one? All right. Let's shut her down.